All right, let's get started. If you have not done so, again, a reminder, Monday is the last day to submit your groups. By the way, just a clarification on collaboration on homeworks because there was some confusion. You might want to pay attention to this because if you don't, then there might be issues. So, if you are collaborating with two other people on a homework, that's fine, but you have to make sure that your group mates don't go and talk to someone else. Okay? So, whenever you're talking with someone or trying to form a group with someone, first make sure they have not collaborated with anyone else on that homework before you start talking with them. Okay? There have been cases where students talk to a group and then the group couldn't meet, so the student met up with other people. That's not allowed. If your group can't meet, tough luck on that homework. Next time, make sure you form a group with whom you can talk. But once you start collaborating on a homework with your group, you cannot change your group from that point. Are there any questions on that? Does that make sense? Okay. Another point, if by chance you're using Internet Explorer or whatever the Microsoft thing is called now, Autolab does not like it. It will not accept anything from you. So make sure you use, I guess, pretty much anything else works, but not Microsoft. It was not my decision. That's how Autolab is built. So. All right. Homework 3 is out. There are two important things that I want to stress, or maybe three. So the first one is, this is probably one of the homeworks where the support page that's linked is very, very important, especially if you have not worked with matrices and vectors before. This is all the questions on this homework are based on matrices and vectors, but all the information that you need to solve this problem is there in this support page. So please do go through it if you're not that familiar. Second, question 1 and question 2 on homework 3 are probably the easiest of all question 1 and question 2 in the entire course. So, for example, if you solve it and you think whether it's a trick question, how was it so easy? It was because, well, it was so easy, okay? On the other hand, question 3 is probably the hardest question 3 in the entire course. So it's a kind of a balance. Just so plan accordingly. By the way, that doesn't mean you should start on question 1 and 2 at Thursday, 11 p.m. or something. That's probably still not a good idea, but the question should be much easier. Evan?
When you say that one of the allowed resources is results from a previous course?
Evan's question was, one of the resources it allows results from previous course? Yes, so that is, I'm pretty sure, explicitly stated in the homework policy. So any mathematical result that you've seen in a previous course, you can say blah result from CSE 191, 115, 116 to 50.
Computer science course?
The question is, computer science course now. If it's outside of UB, that's also fine. Just say this was the course that you took outside of you, just because, you know. Okay. Obviously, we don't expect you to learn anything that you've seen before any course. It's not reasonable, and that's definitely allowed. Any other questions on sources, collaboration, homeworks, Autolab, meaning of life, 42, but Steven.
Just curious about your point that this question 3 is not usually targeted at question 3. And if you say that this is probably the hardest question 3 in the course, does that mean that this is probably the hardest homework question?
So Steven's question is, I said question 3 is typically the hardest, and that's true. I said this is, so the question is, this is one of the hardest problems in the entire course. I personally don't think so, but based on history, it appears so. So I think it's a fun question. I will tell you after the homework submitted why I find this fascinating and why I really love this question, but I can't tell you that to you now because that will be giving out more information than I want. Any other questions? I have to ask your name. Han.
Yeah. I use an external library, let's say NumPy for Python. What would be the source of the question?
So your question is, if you're using external NumPy, So are you asking more towards like if you looked up NumPy or you just use NumPy?
Just use them.
If you're using something that Autolab supports, you don't have to write any source. I mean, yeah. It's only if you look up something, then. Anything else? And I'm pretty sure NumPy is supported this year. Evan.
So then in sources, would we include like the SciPy documentation?
So Evan's question was, if you use NumPy, you should probably use SciPy documentation. Good point. Could you please post on Piazza? We'll officially make it allowed source. Cool. Oh, by the way, this was something I'd mentioned. I don't know if all of you realize this. If for whatever reason you look up a source, even though it's not allowed, but you think it's like kind of a thing that should be allowed, put a private post on Piazza saying, hey, can you please approve this? Okay. So what I'll do is I'll take a look. In most cases, it should be fine. I'll make the post public. And since now it's on Piazza, by definition, it's an allowed source. I cannot guarantee. Sometimes I might say no, in which case, well, then you should probably not submit that question. But in general, that's a way to get your sources allowed. Any other questions? Okay. As usual, I'll hand out the solutions at the end of the lecture. Again, if I forget, just remind me. Okay, so we talked about graphs last time. We defined graphs, rated graph, unrated graph, paths, cycles, distances between two vertices. We talked about a graph being connected. So today we're going to look at a specific class of graphs called trees, which I'm sure all of you have seen before in one form or the other, but turns out to be a very useful subclass of graphs. And the definition is fairly simple. A tree satisfies three things. One, it's an unrated graph. Two, it is connected. And three, there are no cycles. Okay, so these are, as long as a graph satisfies these three requirements, it is a tree. And so, is this graph a tree? No. So, for example, this is disconnected, right? Is this a tree? No. It has a cycle, right? So, there is a cycle here. Is this a tree? Yes. So, this is a valid tree. All right. So what we're going to prove today is that any tree with n vertices has exactly n minus 1 edges. You might ask, why should we bother proving? Well, there are two answers. One, because I think it's an interesting fact. But the second one is this is a good way to kind of go through more examples of how to write proofs and things like that. So unlike the book, which kind of does this, I think, in a couple of sentences, we'll spend some quality time going through proof idea and proof details for this. And then, depending on time, we'll get started about our first algorithmic problem on graphs, which is if I give you a graph, can you tell me whether it's connected or not? So designing algorithms for that. Questions? Okay. Today is our lucky day. This seems to work well. All right. So I'll repeat the definition of trees just in case you missed it. So an undirected graph that I'll name T for tree is a tree if one T is connected. Again, remember, connected means there is a path from every vertex to every other vertex in the graph. And T has no cycles. And the result that we want to prove today is a tree on n nodes has exactly n minus 1 edges. I said, it's an interesting fact. Once we approve this, I'm going to tell you even more general statement which kind of tells you even more interesting thing about trees once you know this result. So always, once you have a theorem, always a good idea to check whether it's true, if someone's claiming something's true with an example. So here's an example of a tree. So by inspection, you can verify that this is indeed a tree. And if you look at the number of vertices, there are 6 vertices, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5 m edges, which is exactly n minus 1 in this case. Of course, what the theorem is claiming is it's not just true in this specific example that I drew, but no matter what tree you pick, the number of edges, again, as a reminder, n is always denoting the number of nodes or vertices in a graph, and m is always denoting the number of edges in the graph. Okay. So let's start off with the proof idea. And the idea is, what we're going to start off with is we're going to root this tree. A way to think about rooting a tree is, let's say you actually have a physical manifestation of this graph where every node is a bead and you have a rope connecting the two guys. Right? And so rooting a tree just means you pick up one bead and let it hang in terms of gravity. Okay? That's one physical way to interpret rooting a graph. Right? So what I'm saying is pick a vertex, any vertex in the graph, and root T at R. And so let's say in this case, we pick R to be this node B. What does it mean to be a root? Is, well, you put B up on top, and then everything hangs off, right? So you'll have A hanging off it, D hanging off it, C hanging off it, and then E and F will hang off in C. Okay? Another way to think about this is the root will become your, say, level 0. All the neighbors of the root will become next level. All the neighbors of the first level will become second level, and so on. Are there any questions on rooting? Does it make sense? Evan.
So you're just geometrically moving the tree.
So Evan's question is, am I geometrically moving the tree? Well, for illustration purposes, yes, but not in any, nothing mathematically like that or anything like that. Okay, so doing it geometrically just makes it easier to visualize, but I mean, there's nothing inherent about physicality of pulling it up by one now. Is everyone okay with rooting of a tree? Yeah.
Do you just pick the vertex at random?
So Harshita's question was, do you pick the vertex at random? Okay, good question. I'll first correct you. It's a nitpick of mine. You have to be very careful when you use the word random, because mathematically that's not the same as arbitrary. So if you mean arbitrary, please do say arbitrary. So I'm assuming you meant arbitrary, yes. So the point is, whatever proof that I'm going to talk about, you can arbitrarily pick any vertex as a root, and the proof will just go through. So there's nothing special about any specific vertex that I pick as a root. Any other questions? So everyone okay with rooting? Okay, then I have a question for you. So if I give you a tree on n nodes, how many different rooted versions of the tree can you have? Sorry, who was that? Stephen is right, n. Why is that, Stephen? Right, so the point is, once you pick a root of a tree, everything gets fixed because everything just falls off from gravity. And there are n nodes that you can pick as roots, so there are n possible rooted trees. Okay. All right. So let's write that as an aside. There are n rooted versions of a tree. Okay, so actually there's a procedure that I'll start off over here again. So I'll just repeat this part. So you root t at r. And now notice once you have rooted things, there's a notion of, if you look at any edge, let's say EC, then C is closer to B than E. Right, so again, if you hang things up, something's going to be closer to the root and the other endpoint is going to be farther away. So what you do is you direct the edges away from R. And again, I want to stress this direction or directing the edges is just a technique or a tool that we're using to prove the statement that we want. Our original graph tree by definition is undirected. Okay? So this goes this way, this way, this way, this way, and this way. Okay? So once you root a tree, you automatically direct all edges. And then we're going to prove two things. We're going to prove every edge. Okay, and once we direct a thing, an edge, then the node that the edge is pointing to is called the child, and the node from which, oops, sorry, thank you, from which the edge is pointing away is called the parent. So what we're going to argue is that every edge has a unique child. That is, every edge will only point to one vertex. And then we're going to argue that there is no edge pointing towards the root. So the next thing we're going to argue is R is the only node that is not a child of some directed edge. And again, we're going to argue this formally in proof details, but again, just to say, we pick a root, orient everything away from the root, then we'll argue that every edge points to exactly one node, and the only node that has nothing pointing towards it is the root. Evan.
Is it still a tree?
So Evan's question was, is it still a tree? So this is what I said. Directing of the edges is purely a mechanism to prove things. Okay? Our original graph is still a tree. Now if you're asking, if I give you this directed edge, is this by definition a tree? Then the answer is no, because it's directed. But again, this direction is just for the purpose of the proof. My original graph T is still undirected. Okay. So what I've said is, every edge points to exactly one node, and every node that is not the root has an edge pointing towards it. So there's a one-to-one correspondence between the edge and the child. Okay. So this implies number of edges. Okay, so this is the set difference operator. So this means this is the set which has everything in V except this set R. And again, remember, this is the size of this set, right? So this is n minus 1. So this is the basic idea. What I'm going to do next is kind of drill through this and kind of make it more formal. Okay? But any questions before I go on to talk about the proof details for this one? Okay. So let's write the details. So as before, we're going to pick a vertex R in V and root T at R. So the first observation, which I'm not going to prove but leave as an exercise for you guys to work out at home, is for every edge UW in E, once you root it, one of them is closer to the root than the other. Then one of them is closer to R than other. And what do I mean by closer? I mean it in terms of the distance that we defined last time. So recall, the distance between a node and a root in this case would be the length of the shortest path from that node to the root. Okay. All right, so once we have this, every edge U and then direct edges from closer node to the farther node. So for example, if you had an edge UW, and let's say U was closer to R and W was farther from R, then we're going to orient the edge from U to W. As I said before, this would be called the parent. This would be called the child. It turns out once you direct the edges, you can also call this the head, because that's where the arrow is starting from. And this is the tail. Yes, I'm going to interchangeably use parent and head and tail and child. All right, so the way I'm going to prove this is I'm going to state 4 claims. I'm going to leave the proof of 3 for exercise this for you guys again. I'm going to prove how, if we assume all the 4 claims are correct, then we have proven what we want to prove. And then I'm going to prove the last claim. Okay? So, all right. So the first claim is the root R is not the head of any directed edge. The second claim you're right, thank you. Oh. Okay, yes. In the book, they might have switched, I might have switched head and tail from the book. So, so actually just to be the safe side, I'm just going to use child and parent. That way I'm sure I'm on the correct notation. Sorry about that. The second claim is every directed edge has a unique child. The third claim is that every non-root vertex is the child of at most one edge. And the final fourth claim is that every non-root vertex is the child of some directed edge. So while you process this, let me give you some commentary on why these 4 claims would be enough. So what claim 3 and 4 are saying together is that every non-root vertex is the child of exactly one directed edge. Right? Claim 3 is saying it is the child of at most one directed edge. Claim 4 is saying it's the child of at least one directed edge, right? So if it's the child of at most one and at least one, then it has to be exactly one. Okay? So 3 and 4 together imply that every non-root vertex is a child of exactly one directed edge. Claim 1 is saying root is not the child of any directed edges. And claim 2 is saying every edge has a unique child, right? So what all of these mean is there is a one-to-one correspondence. So claim 2 means there is a one-to-one correspondence between each edge and its child. Right? There's a unique, for every edge, there's a unique child. The other claim say is every child corresponds to exactly one root vertex. So every edge has a unique child. Every unique child corresponds to a unique non-root vertex. So that means every directed edge has a one-to-one correspondence with all non-root vertices in the graph. Okay. So claims 1, 2, 3, 4 imply there exists a one-to-one correspondence between the edge set and the set of all non-root vertices. And so one of the implications of a one-to-one mapping is if you have a one-to-one mapping from a finite set to another finite set, they have to have the same size. So this implies the number of edges is same as, which is equal to m, is the number of non-root vertices, which by definition is n minus 1. Okay? And so this would prove the theorem we wanted to prove. Of course, we still have to prove the 4 claims that we stated. So as I said, you'll prove claim 1, claim 2, and claim 4 as exercises at home. We are going to prove claim 3 next. But before I start proving claim 3, talk to your friends for half a minute, Let me know if any questions so far. If not, oh, there was a question. I have to ask your name first. Alex?
What's the difference between claim 3 and claim 4?
So the question is, what is the difference between claim 3 and claim 4? Claim 3 is saying there is every non-root vertex is a child of at most one edge. So it could be 0, 2. Okay? Claim 4 is saying every non-root vertex is the child of some edge. So it could be the child of one edge, it could be the child of 2 edges, or even more. What both of them say is, you're saying one is either 0, 1. The second one is saying it's 1, 2, 3, da da da. So the only thing that can happen is exactly 1. Okay, so this is actually a common trick if you want to prove that a certain quantity is exactly equal to blah. You first prove that quantity is at most blah, less than equal to blah. Then you also prove it's greater than equal to blah. And so that together will imply it's exactly blah. All right, so talk to your friends for half a minute. Let me know if any questions. If not, we'll go ahead and prove claim 3. right. Harshita, you had a question. All right, so Harshita's question is, what are these V and R signs? Okay. So this is the set difference notation. So if you have a set A minus B, this is the set of all elements in A such that A is not in B. Okay. So if you look at the Venn diagram of A and B, this is A minus B. This just means it's a singleton set which has only R inside it. So what this is saying is a set of all vertices except R. Any other questions? All right, so let's prove claim 3. So again, we want to argue that every non-root vertex is a child of at most one edge. So what I'm going to give you now is somewhere in between a proof idea or proof details. And since you guys have already submitted at least 4 proof questions, I'm going to slowly start moving towards only talking about proof ideas from now. Okay. So this is, as I said, somewhere in between what would be a valid proof idea or proof details. So any guesses what kind of proof technique we'll use? Contradiction. As I said, you know, whenever I ask this question, you said contradiction, you're 90% going to be right. All right. So we're going to do proof by contradiction. So to prove by contradiction, we have to assume the negation of what we want to prove. So we want to argue that there is at least one vertex which is a child of 2 or more edges. Okay. So for the sake of contradiction, assume vertex U is the child of two directed edges. So here's my U, and maybe there's an X and there's a Y, and they both point towards you. Okay, so let's say this is the case. So now consider the situation in T. Well, what's the situation in T? We're claiming there's an edge from X to U and Y to U, but there's no direction, right? So U to X and Y to U. Okay. And as I had mentioned, when you were proving things, your proof should use all the properties that are there in the problem statement. So we said we're going to assume T is a tree, right? So we have to use the fact that it's undirected, which is what we are doing now. We also have to use the fact that it's connected and use the fact that there's no cycle, right? So we're going to use all 3 to come up with a contradiction. So since T is connected, implies there exists an Rx and Ry paths. Again, why is that? Because it's connected, that means X and R have to be connected, and Y and R have to be connected. Evan.
Are you moving into proof details now?
So Evan's question, so as I said before, this is this weird hybrid between the 2, right? Yeah, so let me finish this, then maybe I'll speak a bit more to what would be a proof detail for this and what would be proof idea. So what that means is there is a path from R to X and R to Y. So the squiggly lines means that there could be more than one edges here. But note that UX, and then you take the path to R, and then you take the path to Y, and U is a cycle. Okay? And so that implies that contradicts the fact that T has no cycles. And so that's it. So again, before I go into what would be a proof idea and proof details, any questions on this argument? No? All right, so the question was, why is this not a proof detail? And I said somewhere in between, and you're almost there. What would you have to do is kind of write this down a bit more formally instead of just drawing with pictures. So in this case, a proof idea would be you could have just drawn pictures. You could have said, let's assume this happens. Then since T is connected, then this happens, and this is a cycle. And that's a contradiction, and that would be a good enough proof idea. And the proof details would be pretty much all of this, but now you write this bit more formally. Instead of just saying there exists Rx path, you say let P1 be the path from R to X, let P2 be the path from R to Y, then consider the cycle U followed by nodes in P1 followed by Y, followed by nodes in path in P2, then followed by U. Okay, so if you write a bit more formally, that would be enough for a proof detail. Richard.
Just like actually write it out, like with proof idea and proof details, so that we don't get it wrong.
Sorry?
Because you know how on the homework we get like a small amount wrong for the proof details to provide this to get points off? So like I'm not exactly understanding what you mean by Java graph or proof ideas and proof details.
Are you asking you don't understand what it means to draw a graph for proof idea? Or?
I don't understand like where you put the difference between proof ideas and proof details.
All right, so here's the generic answer, and again, I don't have a specific formula that you can apply to everything and it will automatically tell you whether it's proof idea or not. But here's the basic thing. So proof details hopefully should be clear. It's like a clear-cut, airtight mathematical proof, right? So a proof detail should be something that even if I sit on it for 2 hours, I should not be able to deduct any points. That's an ideal proof detail, right? There's nothing, every I is dotted, every T is crossed. It's like an air-clad mathematical argument, okay? Proof idea is, I want you to give me a summary of your actual proof details, right? Because typically, in a proof detail, there are 1 or 2 main ideas. So what were the main ideas here? A, we're going to use contradiction, right? B, we're going to say if that happens, then there is a path, there are these 2 edges, XU and YU. And then say we're going to use the fact that T is connected to come up with a cycle. So that's kind of the summary of my argument. And the proof details in this case is you're going to flesh out each of those steps. So that makes.
Like in terms of the class, like can you actually write it out separately?
So are you asking me to write them separately now here? So I'm short of time, so that's why I said I do not have the time, I will not have the time for the rest of the semester to write out separate proof idea and proof details just because there's not enough time. So I'm slowly transitioning into a part where I'm just going to do proof ideas. If you want the proof details, go look up the proof in the book. The book will have the proof details. Okay? Evan.
This whole thing is just a proof idea.
So this whole thing is not, I shouldn't have said this, right? So this is, yes, so the mathematical correct answer is yes, this is a perfectly valid proof idea.
Okay.
Okay? It might not give you the full points for proof details quite, right? Because there's some small things different. But this is definitely a valid proof idea. Any other questions? Mark.
The cycle if the paths are directed.
So Mark's question was, your Mark, right?
Yep.
Okay. Can you have a cycle if this path is directed? So no, right? So if you look at the way things are, you'll have if you're looking at the corresponding directed guide, the original tree, you will have a corresponding directed path from R to X and R to Y. So you have 2 directed paths going like this, which is not a cycle. But that's why I said, you're going to talk about the original tree now, where there's no directions. Right, so you have this directed thing, then you realize, aha, in my original graph, I don't have any directions, right? So I have 2 undirected paths from R to U, and that gives me my cycle. Any other questions? All right, so it turns out there is a much more interesting, more general theorem which I'm not going to prove, but something that's true. It says the following, so let T be an undirected graph. Note here, so far I have not said that it's connected or has no cycle, so the fact that I'm using T doesn't necessarily mean that it's a tree. Then any of the following two properties implies the third. So what are the three properties? The first is that T is connected. The second is T has no cycles. And the third one has T has n-1 edges. So exactly n-1 edges. So note that theorem, the first theorem, what it's saying is if you have 1 plus 2, which along with the fact that it's an undirected graph implies it's a tree, that implies 3. But here what it's also saying is if you pick 1 and 3, that is T is connected and it has exactly n-1 edges, then it necessarily implies that it has no cycles. Also, if you say that it has no cycles and it has exactly n-1 edges, then it has to be connected. So there are three conditions. If any two of them are satisfied, the third is true. However, if only one is satisfied, then it's not necessarily the case the other two will be satisfied. Any questions? This is pretty much all that I wanted to talk about the basics of graphs. Basics of trees. And so any questions on basics of graphs, paths, cycles, connected, not connected, trees, rooted trees? All right, good. So then what we'll do is now move on to some algorithmic questions on graph. So in the remaining 7 odd minutes, we're going to talk about the following algorithmic problems. So as I mentioned before, we want to check whether a graph is connected or not. So what does this mean? I give you, say, an undirected graph, and I want to argue, and your algorithm should say whether the graph is connected or not. So you might ask, why would I be interested in this? This problem, for example, turns out to be very useful if, say, you are setting up an ad hoc network, right? So you have a bunch of, say, mobile devices, and you're setting up an ad hoc network. So one of the basic things you would want from an ad hoc network is you should be able to send a packet from any node to any other node. Right? So in other words, there should always be a sequence of hops so that you can go from any one node to the other node. I.e., you want to check that if you look at the graph that you are trying to develop through these interconnections is actually connected. Right? All right, so there are certain things you can do to try to check whether the graph is connected or not. For example, if it were here, you can do it by inspection, as we already said, and we say, well, no, this is not connected because the last vertices on your right are not connected to any other vertex on your left. Okay? So this is well and fine, but if I just give you a huge graph, there's no way you can say it by inspection, right? So you cannot look at a graph, at least with your human eyes, and figure out that they are connected. So in particular, if I say, well, there's that vertex S and there's that other vertex T, can you tell me whether they're connected or not? You can say yes, and I'll say okay, you'll say no, and I'll say okay, I have no way to tell whether you're lying or not, right? So what we want to do is not be in this situation, and come up with an algorithm that we can prove is correct, right? So you want to come up with a provably correct. So instead of checking whether a graph itself is connected, we're going to have a slightly simpler problem. I give you a graph and I give you two designated nodes. Let me call that S for, say, source and T for terminal. And I'm going to ask you the question of whether S and T are connected. Okay. So if you can answer this question for every possible pair S and T, then you're good, because once you have an algorithm for that, you run this algorithm on all possible pairs, and then you can check whether the graph is connected or not. So what would be the dumbest brute force algorithm you can think of to check if I give you a graph G and two vertices S and T, whether they're connected or not? I forgot your name. Brian.
Generating every possible path and
Perfect. So you want to generate all possible paths. The easiest way to do that is just list all possible vertex sequences. And the point is, remember, you can only look at simple paths, so you can know, for example, that you don't have to look at sequences of size larger than n. And given the sequence, first check if it gives you a valid path, and if it gives you a valid path, check whether the endpoints are S or T. Okay? So the issue is there are lots and lots of these sequences. There are n to the n. If you want to be a bit more careful, if you look at simple paths, there are only n factorial sequences because all the nodes are distinct. Right? But of course, as we've seen before, this is too bad. This is not going to scale. Right? Definitely not going to scale at, like if you wanted to answer these questions on the internet graph, for example, or even the Facebook graph. Right? This is too big. I mean, I can draw a graph by hand in which this algorithm is not going to terminate. So the motivation for this algorithm is, I don't know if it's a problem for you guys, but my father is fairly old, so he discovered email a few years back. I just keep on getting the spams. Like one of his friends is something, it just goes out to everyone in his inbox, right? So here's the basic idea. It's actually a theoretically studied routing algorithm in networks called the flooding network. And so the idea is you basically check for everyone that's connected to you. So say you pick one vertex and they have one token, and you send that token to all of your friends. Then friends will pass on those tokens to their friends and so on and so forth. Right? And if this way a token goes from S and reaches T, then you know that they're connected. So kind of, let's skip this. How many of you have seen breadth first search before? All right. How many of you have proved anything about breadth first search before? All right, so that's what we're going to do. But as a quick reminder, here is the breadth first search, how you would use breadth first search to check whether S is connected to T or not. You build layers successively in breadth first search. So your very first layer, which we'll call L0, just has a start vertex S. And at any point of time, if you have already constructed J up to layer J, you look at all the neighbors of vertices in J that are connected directly by an edge that you have not considered already. Okay? And add those guys to the next layer. Okay? And you keep on doing this till you cannot add a new layer. And the moment you're done, then you're done. What you can prove, which we are not going to prove in class, but it's proved in the book, and I highly recommend you go ahead and look it up, is if you look at all the nodes in layer J, they'll be at distance exactly J from the start vertex. So this is an interesting property that's useful. And so, as I said, this is an exercise that's a good thing to try. If you have not proven anything about BFS, good first thing to try to prove to yourself. Okay? I'll hand out the solutions, and I'll see you guys on Monday.